Welcome. We are in the middle of this exercise now, which we said would take some time to derive, and to make it effective we are deriving it together. The exercise that we saw in the last class, we began in the last class, was starting with the Gibbs-Duhem equation, show that summation over Ni d ln gamma I equals 0, and we arrived at a point where all other terms vanished and we were left with summation over xi, the inside sum, this when this is varied, the whole range of k is taken into account and then this is varied and so on. So, summation over k dou mu I by dou xk at constant Tp xj dxk equals 0. Okay, we have arrived at this stage, equation 4a7 at the end of the last class. This class we will move forward, again we will do it together because this one helps clarify many different aspects and their ways of representation and so on and so forth. So, you would develop much better ease if you do this yourself or if you are able to do some parts of it. So, let us work together on this. Now, we know from equation 4.8 that mu I equals mu I hash plus RT ln gamma I xi. This is the definition of mu I for a non-ideal solution, and this is what we are going to take forward. We will derive it for the most general case, the non-ideal solution case. If we substitute 4.8, equation 4.8 in the previous equation 4.a7, we had brought it down to a simple form of this. We are going to substitute mu I with the expression in terms of mu I hash and gamma I xi and so on. Let us do that. I will show you one step and leave you to work through a few more, and while doing that I am going to drop the terms that are held constant in the partial derivatives. We are very clear that the temperature, pressure and all other mole fractions except the one that is taken for the differentiation are held constant. So, that we will take for granted now in the remaining part of this derivation alone, just for the ease of writing, because otherwise we will have to write so many different terms being held constant in each partial derivative there. So, if we do that, this becomes x1, this is the first term, x1 dou mu I dou xk it was. So, dou mu 1 dou x1 dx1 dxk plus dou mu 1, this is I, this corresponds to I, therefore, that remains at 1, dou mu 1 dou x2 dx2 plus so on until dou mu 1 dou xp dxp. This is just the first term, and then when we change this, we are summing over i's. So, that is what brings in the second term. Summing over k's is what results in the term in the square brackets. So, let us look at the second term, x2 dou mu 2 dou x1 dx1 plus dou mu 2 dou x2 dx2 and so on till dou mu 2 dou xp dxp. What I meant by dropping the terms is we need to write here constant Tp xj and so on. That is what I am not going to do here, just for ease of writing, but it is well understood here. So, there is no difficulty, and so on. You go on by changing the I term to cover all i's and so on till xp dou mu p dou x1 dx1 dou mu p dou x2 dx2 and so on until dou mu p dou xp dxp. So, this is what happens if mu I have still not substituted mu I in terms of mu I hash plus RT ln gamma I xi into equation 4.a7. What I have just done in this step is to expand 4.a7 to show you all the terms, the complexity of that particular term, the last term on the left hand side, if you expand it will contain all these terms, of course equal to 0. Now, let me show you few more steps. Okay, let us call this equation 4.8, and let me show you a few more steps before I leave you to work some of the things out. Now, we will substitute mu for mu I in equation 4.8 using equation 4.8, and note, this is important, note that mu I hash is a function of temperature and pressure alone. See what that means in terms of the partial derivatives in equation 4.8, that is a big hint, but gamma I is a function of temperature, pressure, and composition as represented by x1, x2 and so on and so forth in terms of mole fractions at this stage. Earlier we had represented composition in terms of mole numbers N1, N2 and so on. Here we have brought it down to mole fractions, which makes it a little easier to work with, and I will leave you with this for about 15 minutes. Okay, I would like you to substitute the expression for mu I from equation 4.8 into equation 4.8 and realize that mu I hash is a function of temperature and pressure alone, whereas gamma I is a function of temperature, pressure and composition, and let us see where you get. Substitute, then see what terms go to 0, see what terms can be cancelled out if at all, and see how it can be reduced to its minimum representable form. Go ahead please, take 15 minutes to do it. let us continue. You would have reached a certain stage if you had gone enough ahead, you would have gotten down to a very compact kind of a representation. I do not know whether they have gone that far. Let us see at least some of the steps before I leave you again to do things yourself. The partial derivatives in equation 4.A8 are with respect to mole fractions, and therefore the terms corresponding to the derivatives of mu I hash are going to be 0, because mu I hash is only a function of temperature and pressure and not of composition. Therefore, if you take the partial derivative with respect to the mole fraction, that is going to be automatically 0, because it is a constant value with respect to mole fraction. Therefore, you can just drop all the mu I hash terms completely, and only the partial derivatives of the term RT ln gamma I xi are of relevance here. Okay. Let us see what happens if you put that in. To again for ease of writing or not taking up too much space and not getting confused with the various terms, I am just going to take the first term. Okay, I am going to write the first term, develop the first term completely with the clear understanding that whatever goes with the first term is going to go with the other terms, they are all very similar. So, if we whatever we write and bring it down should be applicable for the other terms also. So, let us do that at least to a certain stage. What I mean by the first term is the entire term in the square brackets on the left hand side of equation 4A8, which is this, 4A8 is this. So, this is the term including x1, that is x1 times whatever is there in the square bracket. This is what I am going to take up first. As you can see, all the other terms here are all similar to the first term. So, the same form should be applicable for the other terms also. That is the reason I am just going to consider the first term. If I do that, now just a mere substitution, it is RT ln gamma 1 x1. So, RT is a constant that can be taken out. We will assume that the RT has been taken out here, anyway the right hand side is 0. So, that is going to go to 0, that will come later. So, x1 dou ln gamma 1 x1 by dou x1 dx1, this is whatever remains of that mu 1. Mu 1 was mu 1 hash plus RT ln gamma 1 x1, mu 1 hash went because mu 1 hash is not a function of x1, and RT has been taken out as a common term in all these expressions and kind of cancelled with 0. Therefore, what remains is ln of gamma 1 x1 dou the partial of ln of gamma 1 x1 dou x1 dx1 plus dou ln of gamma 1 x1 dou x2 dx2 and so on till dou ln gamma 1 x1 dou xp dxp. Can you do the math here? This is, as you can see, this is a composite function, it is a derivative with respect to x1. What would you get if you do this derivative? Or probably I will show you another step before I leave you alone. What I essentially meant was using the chain rule there, chain rule for differentiation, first function into derivative of the second function plus the second function into derivative of the first function and so on. You know that this is function of a function, therefore x1 into the derivative of ln would be 1 by that argument. So, 1 by gamma 1 x1 times dou x1 of gamma 1 x1, which becomes gamma 1 dou x1 by dou x1. We will just keep this term for now for completeness. I know it is 1, but we will keep this term so that there is some form that arises as a part of keeping that there, we will keep that there, plus the second one x1 dou gamma 1 by dou x1 dx1. Similarly, this one would be the ln part of it would be taken care of by 1 by gamma 1 x1, and then you have gamma 1 x1 remaining. So, gamma 1 dou x1 by dou x2 plus x1 dou gamma 1 by dou x2 dx2. Now, you get the hang of it and so on. What I would like you to do is take the next 10 minutes and reduce this to a nice compact form. Okay. It's essentially algebra that I would like you to do, cancelling the terms that are common and combining them into a form that would take care of combining many terms together and so on. Take the next 10 minutes and do that please. It's a straightforward exercise, this one. It will take time, of course. Go ahead please. Okay. Again, if you had gone all the way, it would have just gotten a very small or a compact term left. Let us see how we get to that. This of course was equation 4.A9, our numbering scheme, which can of course be expressed as, you take that gamma 1 x1 inside, you will get x1 into 1 by x1 dou x1 dou x1 dou x1 plus 1 by gamma 1 dou gamma 1 dou x1 dx1. This is the first term inside the brackets, plus again there is a gamma 1 x1 in the denominator there earlier. If you take that inside, you will have 1 by x1 dou x1 dou x2 plus 1 by gamma 1 dou gamma 1 dou x2 dx2, and so on till you reach 1 by x1 dx1 dxp plus 1 by gamma 1 d gamma 1 dou gamma 1 dou xp dxp. This also is partial. We will call this equation 4A10, and the first term, if all the first terms in the square brackets of equation 4A10 are taken together and all the second terms in the square brackets are taken together, what I mean by that is this was 4A10. So, we will combine 1 by x1 dou x1 dou x1 dx1 plus 1 by x1 dou x1 dou x2 dx2 and so on, plus 1 by x1 dou x1 dou xp dxp. This is still inside the flower bracket. That would be one combined term. The other combined term is going to be 1 by gamma 1 dou gamma 1 dou x1 dx1 plus 1 by gamma 1 dou gamma 1 dou x2 dx2 and so on till 1 by gamma 1 dou gamma 1 dou xp dxp. If we combine this, this is what arises, and what I would like you to do is spend the next 5 minutes looking at this and whether you can write this in a compact form. I am sure quite a few of you are seeing this already. What can this be written as? Just one term, that is what I am looking at, and this just one term. Okay. Take the next 5 minutes, even if you need to juggle your memory and come to some form. What does this look like? If you use this 1 by x1 dou x1 dou x1, or let us look at this might be easier to look at, 1 by x1 dou x1 dou x2 dx2 and so on and so forth, or just this alone, how can this be combined, and then what does this remind you in terms of an expansion of a function in terms of its partial derivatives, the total derivative in terms of its partial derivatives. These are the hints that I am going to leave you with for the next 5 minutes. Go ahead please. okay. I am sure all of you would have gotten it by now. You know that 1 by x1 dou x1 is nothing but dou ln x1 dou x1, right. So you have dou ln x1 dou x1 dx1, dou ln x1 dou x2 dx2, and so on till dou ln x1 dxp dou xp dxp. And what is this? This is nothing but an expansion of the total differential d of ln x1 when x1 is a function of x1 x2 x3 and so on till xp, that is it. So this becomes d ln x1, this becomes in the same fashion d ln gamma 1, and of course you have an x1 here, therefore this becomes x1 into d ln x1 plus d ln gamma 1, and this is just the first term, remember that. We will call this equation 4a11, and as mentioned that is just the first term. All other terms are going to reduce to that compact form. In other words, it is going to be, the first term is going to be x1 d ln x1 plus x2 d ln x2 and so on plus xp d ln xp. This can all be combined together, plus x1 d ln gamma 1 plus x2 d ln gamma 2 plus xp d ln gamma p. You would be able to see this quite easily by expanding this, x1 d ln x1, the second term will be x2 d ln x2 plus d ln gamma 2 and so on and so forth. So if we combine all these terms together and all these terms together, we are going to get this as the expanded form. Now take a look at this, it is very nice here, equals 0, of course on the right hand side we will call this okay, we are not going to give a number to that, but also note this is x1 d ln x1, x2 d ln x2 and so on and so forth, and hopefully you would be seeing the light at the end of the tunnel. Whatever we needed to prove, we are almost there. This can of course be written in a compact form as sum over I xi d ln xi plus sum over I xi d ln gamma I equals 0. Let us call this equation 4a12. So this is what we need to prove is 0. Therefore now explicitly we need to prove that this is 0. This looks complicated, but it is not. Now let us expand this d ln gamma xi again in terms of this xi d ln xi is nothing but xi into 1 by xi dxi, d ln xi is nothing but 1 by xi dxi from the definition, therefore which is nothing but dxi because xi and xi are going to cancel out. And now if we take the sum over all terms, before that let us call this equation 4a13. Now if we take the sum over all i's with the note that sum of all mole fractions is 1, which is a constant, here is how it goes to 0. This is sum over all dxi over I, remember this is what was left over here dxi and dxi, and we need to sum over all i's of dxi, and therefore this is by the commutative property. In other words, d is a differential, the difference amounts, and therefore sum of the differences is nothing but the difference of the sums. It's the commutative property holds here. Therefore d of sum over xi, and what is sum over xi? It's nothing but 1 because the sum of mole fractions equals 1, and derivative of a constant we know is 0, and therefore this goes to 0. Equation 4a14. Well, we are almost done. Therefore equation 4a12 can be written as sum over ni d ln gamma I or xi d ln gamma I, which can be written as ni d ln gamma I equals 0. Equation 430. Okay. Okay. Now I think we should stop here, we are out of time anyway. need to adjust in the working times a little bit. When we start up the next class, we will see how to use this, this is what we had proved as an exercise, how to use this to relate it to find or estimate activity coefficients. We will meet then.